Hello physics students. So in the last video, we used differential equations to determine the current as a function of time in circuits that contained an inductor. But the circuits we analyzed were all simple. They only had one loop. Like in one case, we had a loop with a battery, a resistor, and an inductor. And when we solved for the current as a function of time, we saw that it was that rising function, that 1 minus exponential that began at 0 and asymptotically approached the final value of f over r. Then we analyzed another circuit. It was also a single loop, this time with just an inductor and a resistor, and the current began at some initial value, and we saw that then it decayed as a simple exponential function down to 0. Today what we're going to do is we're going to analyze circuits that are more complicated. Complex circuits that have parts that are in series, parts that are in parallel, all mixed together. Now to analyze such a circuit with a differential equation and get the current for all time is too complicated. It's beyond the scope of this course. So what we do in this course is we only analyze the circuits in the beginning, at the very start, when the switch first closes and turns the electricity on, and then at the very end, when the inductor reaches its final state. Now, we've already done an analysis like this with capacitors. So what I'm going to do is sort of piggyback, review what we studied with a capacitor, and then add to that a similar analysis with an inductor. So that's basically how the board is structured here. The title's a little small, a little cramped, Inductors and Combination Circuits. Maybe when you copy it on your notes, you can make it bigger. But we have an analysis with capacitors going across and inductors going across on the bottom to compare. So the first thing, the capacitor. As you remember, it's two metal plates, any shape you want. And when the current comes in, this plate will become positive and this will become negative by the same number of coulombs. But in the beginning, initially we say, and that means at time 0, right when the switch first closes and turns the current on. Since the capacitor is uncharged, maybe we could add that, Q equals 0, then there is no restriction to the current coming in, because if I want to pull electrons away from this plate, if I want to pull them away from this plate, then the plate is neutral, so it's easy to pull electrons away. But later, we see that when this builds up a positive charge, if I want to pull more negative charge away this way, it's attracted to this positive plate. So it becomes harder and harder to pull electrons away. So in the beginning, there's no restriction. But after a long time, when the capacitor reaches its final state, in other words, t approaches infinity, the capacitor blocks the current, so we consider it just as a blockage. And again, a reminder that the concept of infinity in physics is relative. This could be a millionth of a second, and the capacitor is full, and we'd say that's t going to infinity for the circuit. Okay? Compare that to an inductor. Now, inductor, coil of wire, and then when we flip the switch, what we're trying to do is drive current maybe to the right, and so that's a di dt. We're trying to increase the current driving it to the right. That means the inductor induces a voltage to try and prevent that from happening in the backwards direction against the current. So what that means is that initially at t equals 0, and I guess maybe I could squeeze it in over here, that means the current is 0 at that moment. The inductor will act like a blockage with that backwards voltage on the current. But after a long time, so it blocks the current only initially, but it does allow it to increase just gradually instead of jumping up instantaneously. So it does gradually allow the current to increase, and then after a long time, the current reaches a constant value, so there's no di dt and there's no voltage in the inductor, so that means there's no restriction. The current flows after a long time freely through the inductor. So you may already notice the behavior is swapped. In the beginning, the capacitor has no restriction, but in the beginning, the inductor is a blockage. After a long time, the capacitor is a blockage now, but the inductor provides no restriction. Okay, so let me first create a pause to allow you to copy this down. But again, try and structure your notes so you can go across as I have, so you could directly compare the behavior. Maybe you want to turn your paper into like a landscape portion or arrangement. So go ahead and copy these notes down. Okay, so now let's take a look at two circuits we're going to analyze. We got a battery source, a switch, and 3 resistors. These two are in parallel, and then those are in series with this one. But in this branch, I've inserted a capacitor. And this is the same exact circuit, but in the place of the capacitor, I've inserted an inductor. So again, parallel, in series with this one, inductor in that top branch. So let me create a pause to allow you some time to copy these two circuits down. All right, so moving on. What we're going to now do is analyze these two circuits in the beginning and at the end. So you see t equals 0, t goes to infinity. So as I said earlier, in the beginning, the capacitor allows charge to flow freely through this through this part of the circuit, so it acts like a wire. So basically, it's like not even there to the battery. And then we could find the current in such a circuit by doing total volts over total resistance. And what I did is I found the equivalent resistance of these two using this reciprocal rule. And then that one resistor of these two right there is in series with R1. So that's the total resistance. I'm going to call that IA. Just for later for to graph. Now, let's skip over this for now, and then I want to just look and continue on with the capacitor analysis to sort of create a little continuity. Now, after a long time, in other words, t goes to infinity, the capacitor becomes full, so it blocks current from going along this path. In other words, R2 gets now deprived of any current. And so the circuit behaves to the battery like this. It's as if R2 and the capacitor aren't even here anymore to the battery. So the only part of the current where current's driving through are these two resistors. And so the final current is voltage, total volts over total resistance, simple series circuit. And I'm just going to label that IB for convenience for later. Now, so this is all you have to do for the capacitor in a circuit that looks like this, is just analyze it before, analyze it after, get the currents before and after. However, you might still have to create a graph or graphs to show a conceptual understanding of what happens as time goes on, how this evolves into this. So, but of course, you're not getting a function like we did yesterday in the last video. We're just creating a graph to show the pattern. Obviously, what's going to happen is the current in resistor 2 will gradually die to 0. So that's what I have in this graph over here. The current is gradually starting at some initial value, which we could find if we wanted to calculate. We could get the current in there if we wanted to analyze. But it does go to 0, as we could see. Now, in resistor 1, what happens is the current starts here, and then it gradually decreases to this. And so what we could do is we could plot that it starts here and ends there. But as we know with capacitors, things exponentially reach their final value. So you would just show like a decay asymptotically approaching current B. We have no information about this time axis because we don't have a formula, but we know sort of conceptually that the current in this resistor will gradually get smaller and smaller and approach its final value like that. So let me create a pause to allow you to copy these, the rest of this analysis over here. All right, so now we're going to look at a similar analysis with the inductor. And as I said already, in the beginning, this time, the capacitor acts like a free pass for the electricity, but in the beginning, the inductor acts like a blockage. So no current can get to R2. So I draw the circuit like this. I don't even sketch those because to the battery at the t equals 0, they're invisible, they're not felt. Okay, so the current is, using Ohm's law, total volts over total resistance. That's a simple series circuit. There we go. Notice it's the same current as we have over here. Right? Now, after a long time, the inductor, instead of being a blockage after a long time like the capacitor was, after a long time, it becomes like a free pass for the electricity to flow. So the inductor is here, but I'm not drawing it because it's not even felt in the circuit. It's just allowing the current to pass through. So in other words, now the circuit looks like this with all the resistors present and taking current. So the total current will be the total voltage over the total resistance. I find the equivalent resistance of these two in parallel and then add it to this one because they're in series, this arrangement and that one. So there's how I get that expression. That's the final current in this inductor resistor circuit. In other words, notice how it's the same expression as here. So what you should see, note the pattern, is that the beginning of it with a capacitor is the same as the end of the inductor state. Whereas the capacitor, after a long time, behaves like the inductor did in the beginning. The same kind of analysis, it's just that one does the opposite in the beginning versus in the end. You should also be able to create graphs of the currents. Now notice the current in resistor 2 over here starts as 0 because the inductor acts like a blockage in the beginning, and then it gradually increases to whatever it is in this circuit. So we make like a rising 1 minus exponential graph for the current in resistor 2. Again, we could get this final value by just doing an analysis of a combination circuits and figure out the current in this top branch. It's pretty easily done. And so we could even put a value here if we wanted to. But nothing about the time scale. Oops, I forgot to label the time axis here. And here. Okay. And then the current in resistor 1, well, it begins this. This is the initial current in the whole circuit. In other words, in resistor 1, it's this value. And then after a long time, it becomes this value. So in other words, it starts at B, the lower value, and rises up to A, the higher value. So we make like a 1 minus exponential, but not starting at 0, starting at IB. And we sort of just, fill in a curve that's appropriate. So let me create a pause to allow you to copy the rest of these notes down. All right, so that's all you have to do for these inductor combination circuits. Similar to what we did in capacitance, in the beginning, the inductor's a blockage. The whole branch that the inductor's in, just like erase it out of the diagram and analyze the circuit. After a long time, the inductor acts like a free allowance of electricity. So in other words, it's like the inductor isn't even there, and it's just a wire. Redraw the circuit without the inductor, replace it with a wire, analyze all that you need to. That's what the currents are as a function of time at the end for the inductor. All right, so one last piece, though, I want to mention for today. We're not quite done yet. So something that you may have realized, but if you haven't, then let's see. So I showed you this circuit already. So this can be used to, first, when the switch goes into A, it allows the current to build up in the circuit. Then, when the switch goes to B, what happens is the current will start at its I0 value, whatever it was before when the switch was in A, and it will exponentially decay and go to zero. But what that means is that while the current is decaying, it's still driving current through the resistor. And as you know, the current in the resistor creates heat. It creates power, I squared R. And that heat, that is energy. It has to come from somewhere, as we know from the law of conservation of energy. But the battery is now out of the circuit. So while this current is decaying and there's more heat coming out of the resistor, where did that come from? There's only one other thing it could have come from, and that's the inductor. So that means that an inductor, when it has current, because it'll continue to drive it for some time, that inductor has energy in it. And that inductor's energy is given by this expression. We say U, potential energy, is the symbol, U is a symbol we use for potential energy, and the energy in inductor is 1/2 the inductance I squared. So that's the energy that's in an inductor that will eventually get dissipated in that resistor. So there might be a few applications in tonight's homework where you need that expression to figure out the energy in an inductor. And it'll be especially useful for tomorrow's video, which is inductor capacitor circuits. All right, let me create a moment to pause to allow you to copy these notes down. Okay, so we analyzed combination circuits with inductors in them, and we learned about inductor energy. I hope you enjoyed the physics. I hope you enjoyed the video. Go back, review your notes, make sure you understand everything, and I'll see you in the next physics video.